Thank you. Thank you for your presentation. I'm Stella Moreiras. I'm from Argentina. I am a researcher and professor of the University of Cuyo. I'm hoping that we have a good communication. You can hear me well during this talk. Well, I'm going to present some advances in a review paper that we published in Geosciences the last year about debris flow in the Andes. We try to gather all the information about debris flow in this region because 96% of fatality are triggered by precipitation, and if we see a fatal landslide, at least 73% of fatal landslide are triggered by precipitations. So we concentrate in the arid central Andes of Chile, Argentina, between 30 to 34 degree south latitude, and this area comprises the western slope of the Andes that are Chile, and the eastern slope are Argentina, and the area comprises the highest peak of the Andes, Aconcagua Mount, with 6,958 meters above sea level, and we have different geological units along these Andes that we have main cordillera, frontal cordillera, and precordillera. So we have different kind of rock in this portion of the Andes that comprise the Mendoza city to the east and Santiago to the west. So in this region that fall in the arid diagonal segment, the precipitation are related or forced by the behavior of the ITC zone. When this belt go to the north during winter, we have all the humidity that came from the west, from the Pacific anticyclone, and would call westerlies, and all this rainfall affect the Andes region. And during summer, when the ITC zone go down to the south, we receive all the precipitation from the Atlantic anticyclone. If we made a profile, this is a chart from Viale this year in the paper from Frontier. We can see a profile, the elevation of the Andes. This profile is for this latitude, 30 to 32, and this profile is to the south, 32, 34. We can see all the meteorological stations, and the rainfall, the winter rainfall that we receive at this latitude is really very low, 400 millimeters as mean annual precipitation. And to the south, this precipitation increase. We are talking about winter precipitation, the precipitation that we receive from the Pacific anticyclone. We have at least 1,000 millimeters in the western side, and this rainfall is lower to the eastern part of the Andes. So in this scenario, we have the climate is also forced, or precipitation are forced by the ENSO, the warm phase of the ENSO, El Niño, and also the PTO. Here in this illustration, this figure, we can see a large drought that has been affected the area during the last 10 years, with 30% less of rainfall that have generated a lot of fires in the region. And we can see in brown color those affected vegetation, no healthy vegetation, and in light blue a good health of vegetation. So in this region, we have a very contrasted environment, we have a very high topography. We have area that receive high precipitation and other areas that are very arid, particularly in the higher part of the mountain. We have also a different temperature, the higher temperature in the lower part, and the colder or less temperature in the upper part of the mountain. And also we have different kind of glacier. We have covered and uncovered glacier in this area, and that's important to understand the permafrost and perglacial areas of this region. So in this area, we are going to have different kind of debris flow. Normally, these debris flow are generated in very steep slope. They are associated to a stream flow, river, and alluvial fund. As we can see in this chart of Galmont of 1956, we can see that we can have mud flow, debris flow, but also we have hyperconcentrate flow associated to a stream flow. So in the nature, we are going to have all kind of debris flow that can be mixed in the river or in the alluvial fund. Also, we can have hyperconcentrate flow associated to glacial outwards flow and landslide damaged lake overflow. This is a map of the historical event that we could gather from the study area. And as you can see, all these historical events are concentrated along the road where somebody has reported this event that has generated some damage to the road or to some village. Yes, generally the damage are associated to national or international road. So we have at least 400 historical events. So from this event, we can have some data. Normally, the person or the institution reported the damage event, but they don't estimate or don't have information about the velocity or the volume of this event. So when the data could be recovered, we can calculate the relation between here the volume in this graph and the runout. We can see some event, for example, in the Chilean part. This triangle is related to the Parraguirre event in the Colorado River that was generated in the glacier area. So we have some snow or ice incorporation in this event, the same that the event that occurred in Juncal Glacier. So they really have a long run out or a great distance, but the great distance are found for the glove event that are related to the collapse of the ice damming lake. And this event was also a rupture of natural dam that was generated in San Juan in Argentina. This is the event that present the higher runout, but the volume was not so big as those recording for glove event. In this part, this rectangle represent this data. We have the more common debris flow that has been recorded in the area, that as you can see, they move or they take a distance of 9 kilometers until 10 kilometers, no more, and the volume don't reach 1,000 cubic meters. But really the volume are really important to the road and the infrastructures affected by this debris flow. And in this chart, we can reconstruct relation between mean velocity and the runout. And really, we couldn't find a lot of data about velocity, but here there are an inverse relation between runout and velocity. We also reconstruct some spatial distribution inventory map about historical and also event of debris flow. This map is from the Mendoza River Valley in Argentina, and we estimate the mean annual precipitation, the precipitation to generate landslide, the Drake value. We found that normally the number of events are related to those areas affected by El Enso, but the warm phase of the Enso phenomena. And the precipitation for generate this debris flow are really low. We have debris flow when the precipitation is 7 to 10% of mean annual precipitation. We are going to have at least 50% of our debris flow has been generated by this low precipitation. Also, we have had debris flow generated by permafrost melting. Here there is some cases near Aconcagua Park. This is from Aconcagua Park, Los Grises Galley. This is also debris flow generated in the Aconcagua Park. This is La Salada Galley, and this is El Negro. That all these events were generated in the summer of 2015 and 2016, between December to January. Here is represented different belt, different color represent the altitude. These are the date, and the blue dot represent the altitude of the zero isotherm. We can see that the line, the blue lines and this line represent the event. And here we can see the increasing of the altitude of the zero isotherm, and then the occurrence of this event. At least 4 events were recorded in this galley the day following the increase or the climbing of the zero isotherm. In this galley, we can find a rock glacier that the frontal part of this rock glacier falls during the melting of the permafrost. Also in the Negro Galley, we found also an increase of the elevation of the zero isotherm, and also we record 3 events after this episode. And finally, in the Soltera Galley, we also found an increase of the zero isotherm, but this event was also generated by precipitation. So there are 2 causes from this event in this galley. Also, we have found some debris flow generated by permafrost melting in Elqui Valley. In this sector, we couldn't find any record of precipitation. Here we estimate Vergara, estimate the permafrost distribution, and estimate the potential solar radiation. And in this area, also we can find record from the neighbors' meteorological station, and we found that was an increase in all of them of the temperature associated to the debris flow generation. So in this area, we have both an increase of temperatures and permafrost degradation associated to this debris flow. When we are talking about temperature, also we can see that with the temperature, we condition the kind of debris flow that we are going to have. With higher temperature and higher storm precipitation, we are going to generate debris flow and mud flow, or we have a greater probability to generate debris flow and mud flow. And with lower temperature and lower precipitation, it's more probably to generate hyperconcentrate flow. So if we see our study area, we can find that we have some events generating in the upper part of mountain area. Here is a profile in the Mendoza River Valley. Here is main cordillera. This sector is frontal cordillera, and this part is pre-cordillera. We have some events generated in this sector. At least 16% has been generated by thawing or permafrost degradation. In the lower part of frontal cordillera, we have those debris flow generated by rainfall, and this rainfall normally came from the Pacific, so they are associated to the westerlies. And in the lower part of the Andes, in precordillera region, we have debris flow, but this debris flow are generated by rainfall that came from the eastern part, from the Atlantic anticyclone. So in this area, we have different triggering of the debris flow or high discard flow. So for ending on to remark our result in this paper, we found a higher temperature, the elevation or climbing of zero isotherm, the permafrost degradation, the intensification of the ENSO, and concentrate episodes of heavy rains are affecting the slope instability in this portion of the Andes. So thank you for your attention.